Let's conclude our discussion of probability with a summary. As with any summary, many important details will not be included here, but they should be found somewhere in your notes. One of the key things that we discovered and is an important property of probability is that probability falls somewhere between 0 and 1 inclusive. So any student of probability should note values that are not considered a probability. If you run a calculation and you get a value larger than 1, this property should be in your mind, and you would know to go back over your work and correct that. Or certainly anything less than 0 should not make any sense to you at this point. All probabilities are between 0 and 1 inclusive. Okay? Another important topic we mentioned was the law of large numbers. Which said that as the number of times n increases, the number of times we perform a procedure, the relative frequency probability gets closer and closer to the actual probability. Okay, or the book will say tends to approach, but this is what it means just in layman's terms. Gets closer and closer to the actual probability. Now, we can, again, let's say that we understand this through probability that we have a complete understanding about, such as flipping a fair coin. We already know the probability of heads and the probability of tails. The probability of heads and tails is the same, 1/2 and 1/2. But we can run a procedure flipping a coin and show that as we do this more and more and more, we get closer and closer to that 1/2. Obviously, we could flip a coin 10 times and maybe even get 8 heads, and doesn't represent 1/2. But as we flip that coin more than 10 times, in fact 10,000 times it might take to get closer and closer to 1/2. Now, we don't really care about the probabilities that we already know something about, but we use those to understand this. So since we know the probability of flipping the coin, we can then run that procedure and have a better understanding. But what this tells us is that when we do not have any idea of the probability of an event, we at least know this. The more that we run this procedure, the closer we get to the actual probability. And that's why this is so important. Okay, so those were a couple of points we talked about. Then we got into all the different ways we can calculate probabilities. So let's look at the techniques for finding probabilities. Okay, so one that we looked at was the observation technique, or what we called relative frequency. And that's what we're referring to here, that the more we perform this procedure, the closer and closer we get to this relative frequency probability. So in this one, the probability of event A is equal to the number of times A occurred over the number of times the procedure was repeated. And this is what I was calling above that lowercase n, Okay, that's what we're referring to when we say as n increases. So the more we run the procedure, the closer we get to the true actual probability. Okay, so that was one way we said we could compute probability. All right, we also talked about the equally likely outcomes method. Or the classical approach, we called that. And this is the method where we know something about the sample space. We can create the sample space. For example, we could write out the sample space for a couple having 3 children, all the different possible outcomes, and then by looking at that sample space, then we can determine the probability of, for example, our event A maybe being probability of 2 boys, and then we would find the number of ways A can occur. So we look at our sample space and count the number of ways a couple could have 2 boys, and then we divide that by the number of total outcomes. How many outcomes were in our sample space. So when we use equally likely outcomes, then we can calculate this often by creating the sample space and using that to help us with our calculation. Okay? Another method we talked about was complements. We said it's often easier to find the probability of A by using this relationship, that the probability of A is equal to 1 minus the probability of the complement of A. So in any sample space, whatever your event is, the complement of that is that that event did not occur, because those are the only 2 choices. Either A did happen or A did not happen. And the sum of the probabilities of our sample space equals 1 for any sample space. So if these 2 are the only 2 possible outcomes, or they are complements of each other, either A occurred or it did not, then this relationship holds. We also saw that we could rearrange this formula in many different ways. Of course, we could solve for the complement of A, or we could say the probability of A plus the probability of not A equals 1. But in general, this is the form we frequently use for calculating probability. Okay, then we got into the addition rule. And the formal addition rule was the probability of A or B, or was the key word here, was equal to the probability of A plus the probability of B minus the probability of A and B. And that helps us correct for any overlap where we have outcomes that are the same in both A and B, that we would have double counted them. So we make that correction. Now, we did say that if A and B are disjoint or mutually exclusive, if A and B are disjoint events, well, I'll say disjoint, or another word for that is mutually exclusive events, and only if that's the case, then we can calculate the probability of A or B by strictly adding the probability of A plus the probability of B. We illustrated this visually by showing a Venn diagram and saying when this is the case, we don't have any overlapping circles in our Venn diagram. Okay, that was the addition rule. Then we moved on to the multiplication rule. probability of A and B. The word and tells us it's the multiplication rule. That's the probability of A times the probability of B, given that we know A has occurred. And what we said then is if A and B are independent events, and let me make a note about that. That means with replacement is another way we refer to those independent events. Or recall, if we can assume they are independent, then the probability of A and B is equal to the probability of A times the probability of B. There's no condition because they're independent. And don't forget, the way we determine in a problem where they are dependent, but we want to use this rule for independent events because it would make our calculations easier, the criteria that must be met is that the sample size is less than or equal to 0.05 or 5% of the population size. If this is true, then, if true, then we may treat dependent events as independent. And that's nice because the calculation is easier. Recall that we can just, these are all going to be the same probability, and therefore we can just raise them to the to an exponent and make that easier. Okay. The next technique we learned was for a special case called the probability of at least one. And we found that at least one, of course that means one or more, so in any sample space where you're counting things, that means 1 or 2 or 3 or 4 all the way to the highest possible value in your sample, whatever n is. Therefore, the only thing not included is 0. So the probability of at least 1 is easiest found by using complements. That's the probability. That's 1 minus, the probability of none, because that's the only thing left in the sample space. And finally, we talked about conditional probability in its calculation. Conditional that we first talked about with the multiplication rule, but now we talked about how we could actually calculate that, the probability of B given A, and we found that that was equal to the probability of A and B divided by the probability of A. And we also found that the probability of B given A is not the same as the probability of A given B. We said that's the confusion of the inverse. If you get these confused, it's there's a name for that because it's a very common thing. Okay, so that's a summary of the high points of the things we talked about. I want to come back up here and make sure that I'll notate next to this the comment that, which I already have made but didn't write, the sum of the probabilities in a sample space is 1. Okay, that's another very important point that we touched on at the beginning of this discussion of probability. And so perhaps it's a good idea to make that statement here.